Hello and welcome. Curious about data science and how raw data transform into meaningful insight. In this session, we will explore data processing, a crucial step in preparing data for machine learning models. We will cover normalization, a key pre-processing step for improving model accuracy. Min and max and Z-score, essential techniques for scaling numerical data. Proper pre-processing crucial data is comparable, clean, and ready for analysis, leading to better predictions. Plus, we will include code output and visual explanations. By the end, you will understand how to apply these techniques effectively to enhance your model. Let's get started. Data normalization. Normalization is the process of adjusting the values in a dataset to a common scale without distorting differences in the range of values. The goal is to prevent features with large range from dominating others, ensuring equal contribution from all features. Data rating differences. Features in a dataset often they have vastly different scales. For example, comparing feature like age ranging 0 to 100 and income ranging 10,000 to 2 lakh. If left unnormalized, income will dominate model training due to its larger numerical range. Importance in machine learning. Algorithms like k-nearest neighbors, KNN, support vector machines, SVM, and neural networks are sensitive to scale of the data. These algorithms use distance metrics or gradients which are heavily impacted by the differences in a future scale. Importance on model coverage. When features have different scales, model may converge slowly or inefficient, leading to longer training times and potentially suboptimal performance. Why is normalization important? Without normalization, feature with larger range can dominate the model's prediction, leading to bias in favor of those features. Feature contribution, just like consider a scenario with a feature like height in centimeter and income in dollars. The large scale of income may cause the model to overlook height because the range of income is significantly higher. Improve model training by bridging all the features onto similar scale. Normalization helps improve the model's training efficiency and convergence. Like say efficiency increase with normalized data, algorithm can train faster and converge more quickly because the model treats all feature equally. Types of normalization techniques. Normalization ensure that features with different units and scales do not dominate machine learning models. There are two popular methods. Min-max scaling. This method transfers the data into a fixed range, typically 0, 1. Z-score standardization. This method rescale the data by subtracting the means and dividing by the standard deviation, producing data with a mean of 0 and a standard deviation of 1. Min-max normalization. Min-max normalization is uh, data by scaling into a defined range 0, 1, or sometime if required 1 minus 1. This is a particular useful for algorithms that require standardized output values such as neural network and decision tree. One key advantage is that it preserves the original relationship between data point. However, its main drawback is sensitive to outliers. A single extreme value can disproportionately shrink the rest of data. For example, imagine test score range from 50 to 100. After min-max normalization, 50 maps to 0, 0 and 100 is maximum is 1. A score like 75 would be mapped to 0.5. This allows machine learning model to process a value efficiently. This is a code. So we have a sample data and then initialize and normalization for min-max, and that is a plotting area, and then create a figure, plot original data points, and then normalize the points and contact proceeding points. So this is the graph. The blue point is represent to the original data values. The red point, the normalized data values after applying min-max scaling. The dashed lines show how each original values map into the normalized counterpart. The transformation ensured the minimum values 20 is mapped to 0 and maximum value 100 is mapped to 1. Min-max normalization is particularly useful in machine learning models, especially for neural networks where input values should be in a fixed range. And that is the manual results. Z-score normalization, original feature values, and then this is the mean feature values and standard deviations of the feature values. Characteristics center data around zero mean is equal the scale it based on standard deviation. Useful when features are different units are range. Uh, Retains outlier influence unlike mean max normalization. Z-score normalization, also called standardization, transform the data so that its means become zero and standard deviation become one. This technique is particularly useful when the data set contains features with different units of measurements, height in centimeter versus height in kilogram, weight in kilogram. The algorithm assumes a Gaussian distribution, a linear regression, PSA, and clustering. There are outliers, but they should not heavily influence scaling. Unlike min-max scaling, z-score does not constrain value within a fixed range, but instead center them around zero. Z z-score normalization code initialize standards scales to apply z-score and then plot the distributions. Z-score graph, each blue dot represent a data point from the original list, like 20, 50, 80, and 100. And this line is from here. So the horizontal red shades line is mean of data, that is 0. The distance of each point from the center shows how far in which direction a value from the average. Left the red line below average and right line is the above the average. So let's say the 50 is minus 0.28 is goes from here, and then gradually everyone is taking this side. A mean max scaling versus V score normalizations. The features are range difference. Mean max scaling transform values into a fixed range, typically 0 to 1, which is useful when you bounded values. Z-score normalization center data around 0, making it useful for algorithms that assume normal distribution. Outlier sensitivity, main scale scaling is highly sensitive to outlier because extreme values shift the range. If there is a very large or small value that is compressed most of the data into a small spaces. Z-score is normalization reduces the impact of outlier because it is standardized based on a standard deviation, ensuring a more balanced spread. When to use min-max scaling when you know the minimum and maximum values in advance or when data needs to be a specific range pixel intensity in images processing. Z-score normalization when data has different scale, when the algorithm assumes normally distributed linear regression or PCA. The best for Min-Max is commonly used in deep learning, KNN, and deep learning, and model that rely on distance-based measures. Z-score work well for linear regression, PSA, and SVM. And this is a graph, original data set in left side. This is a graph shows raw data sets before applying any scaling. The values range 10 to 100, which extreme outlier are 300. This one. Each data point is labeled, making it easier to track specific values. Most values are relatively close together. The outlier is far away from the rest of the data. Min-max scale data transform value between 0 and 1. The smallest value is 10 and becomes 0, whereas the largest value 300 become a 1. Key observation, the outlier of 300 is a scale to 1. This 300 scale to 1, while most values shrink closer to 0. This can distort the distribution because outlier heavily influence scaling. The spacing between value is not preserved and it was the original data. Z-score normalization center around 0 with the standard deviation of 1. Most values key close to 0 while the outlier 300 is far above the rest. Unlike min-max scaling, the relative spacing between values is preserved. Outliers don't compress under other values, making this method better for dataset with extreme values. Code output and visual explanations. Min-max normalization. Here we have used min-max scaling for simple dataset. Original values are 10, 20, 30, 40, 50. The output transform the smallest values is 10 and 0 and the largest is 50. All immediate values are scaled proportionally between these two twos. And this scaling keep the relative spacing between data points impact the graph of this would be straight linear transformation of the input compressed into a 0-1 range. This method is especially useful when working with models that are sensitive to input magnitude like neural network. Z-score normalization. In contrast, Z-score normalization transforms the same datasets into value based on how many standard deviation each point is from the mean. The mean of this data is 30 and the standard deviation approximately is 15.81. So 10 is roughly 1.2 standard deviation below the mean, while is 50 is 1.26. On a graph, this would appear centered around 0 with the symmetric spacing on other side. Ideal for algorithm that assumes a distribution on rely on distance. Min-max versus z-score normalization. Basic concepts. Min-max transform feature to a fixed range, especially 0 to 1. Normalization, on the other hand, standardized data bias in centering around 0 and scaling used standard deviation. This difference significantly affects how algorithms interpret feature magnitudes. Sensitivity, high sensitive min-max is very sensitive to outlier. A single extreme value can squash the rest of the value into a tight cluster. In contrast, Z score is more robust and treat outlier more gracefully since it's based on the spread of data rather than fixed boundaries. Examples are, for example, imagine house prices if one house cost $1 million while most are 100K and 300K. Min-Max will compress the values too much. With Z-score, a 1 million score house would still show on extreme but would not ruin the spread of others. Similarly, with exam score, Z-score helps in highlights outlier without distorting everything else. Best use for KNN, use min-max when model require input to be in a limited range like neural network or image processing tasks where pixel values range from 0 to 255. Z-score works better than the model depends on distance or assume a distribution like PCA and SVM. Ideal scenarios, if your data set is well behaved with no extreme outlier, min-max will do just fine. But when data is skewed or varied significantly, z-score retain meaningful distance and pattern, making it better choice. Key decision guide. If model are require bounded inputs, you are working in the clean uniform data, go with maximum scaling. Ask yourself if model require bounded input. If yes, min-max does the data have outlier or need to follow a normal distribution. Then go with z-square also for clustering and nearest neighbor algorithm. Z-score is useful more effectively. Quick decision guides. Need values min-max. If your algorithm is modeled dataset strictly between 0 and 1, like a neural network or image pixel data, min-max scaling is the ideal method. It keeps all data within a fixed range, which can be crucial when activation functions are bounded like segment or time. Presence of outliers, min-max scaling can be heavily skewed by outlier. If you have an 2 or extreme values, the entire scale get compressed. Z-score handles its better standardization based on mean and standard deviation, making outlier more monographable without distorting the rest of the data. Distance-based model, KNN, SVM, that is called normalization. Models like KNN and SVM rely on calculating distance between data points. If features are not scaled, one feature might dominate the others. Z-score ensure all features contribute equally by bridging the same scale centered around zero and scale by variance. Normal distribution assumptions, z-score normalization. Again, some algorithms like linear regression, PCA, and naive Bayes assume the input features are normally distributed. Z-score helps meet this assumption by shaping the data to a bell curve structure centered around way which enhance performance and accuracy. Thank you.